Early tech support logs are filled with variations of the exact same call. A user hits a button on their desktop tower, a tray slides out, and they carefully set their coffee mug right on the CD drive. This is not user stupidity. When a person misinterprets a sliding disk tray as a cup holder, we are looking at a failure of the designer to translate human cognitive expectations into the digital system's interface. To understand why these breakdowns happen, we look first to affordances. These are the physical properties of an object that allow a user to implicitly understand how to interact with it. This keyboard highlights the danger of perceived affordances, what the user believes an object does based on its appearance. Notice how the identical physical shape of these two distinct keys induces the exact same thought of action, creating immediate confusion. To correct that confusion, designers rely on the second pillar, signifiers. A signifier is the physical or visual indicator, a printed word, an etched image, or an icon, that explicitly affirms the functionality of the affordance to the user. Once the user understands the signifier and takes action, we enter the third pillar, mapping. Mapping is the necessary, predictable relationship between the specific action a user takes and the resulting consequence in the system. When mapping is unpredictable or broken, the user experience collapses. People will initially self-blame, abandon the tool entirely to seek help, or leave highly critical reviews of the product. To confirm the mapping was successful, the system must provide feedback. This is the immediate, tangible response, whether a visual flash, an auditory click, or a pop-up, acknowledging that the user's input has been received. Speed is critical here. In web environments, the system must provide this visual feedback within 1/10 of a second. Anything slower induces user anxiety and the suspicion that the system has frozen. When affordances, mapping, and feedback align perfectly, they encourage repeated learning. Over time, this allows the user to build a robust, frictionless mental model of exactly how the system operates. Transitioning from physical hardware to the digital screen requires translating those cognitive primitives into software rules. Historically, the standard for this interaction has been the Desktop Graphical User Interface, or GUI. The core philosophy driving the GUI is direct manipulation. Instead of typing abstract command lines into a terminal, users perform physical actions directly on digital objects. The primary characteristic that makes direct manipulation work is the continuous, uninterrupted visual representation of the objects on the screen. The files and windows are always visible. Pointing devices are then used to execute simulated physical actions. Grabbing a file and physically dropping it into a trash bin removes the need to memorize syntax, drastically reducing the user's cognitive memory load. Because actions are rapid and highly visual, they must also be reversible. Commands like undo are critical psychological safety nets. They encourage user exploration by removing the paralyzing fear of making irreversible errors. These mechanics operate within the standard structural elements of a GUI architecture: windows, icons, menus, and pointers, often referred to as WIMP, working alongside discrete buttons and dialog boxes. GUIs do have functional limitations. They require high local memory and processing power to sustain their graphics. Furthermore, they can actively slow down expert users who often prefer the raw speed of a text-based command line interface. Ultimately, GUI design is an exercise in simulating a physical workspace. It leverages our real-world spatial awareness to make digital multitasking intuitive and manageable. The strict spatial rules of the desktop GUI fail entirely when we open an internet browser and enter the web user interface. The core structural difference is that web UIs are not built on the direct manipulation of closed local objects. Instead, they operate on non-linear navigation through a vast, decentralized hypertext structure. Web UIs are defined by heavy multimedia integration, responsive layout designs that must adapt to thousands of different screen sizes, and dynamic content that updates instantly based on user interaction. Their universal popularity stems from platform independence. A website can run on any operating system without requiring local software modifications. The logistical advantages are massive. Web UIs offer easy accessibility via direct URLs, zero installation requirements for the user, and centralized automatic maintenance handled entirely on the server side. This matrix explicitly contrasts the two paradigms. While GUIs rely on local installations, web UIs utilize browsers and automatic updates. This absolute requirement for network connectivity introduces new design constraints to account for variable bandwidth speeds. While GUIs are built to maximize task execution within an isolated local system, web UIs are engineered entirely around information retrieval and continuous, fluid navigation across a network. The primary danger of the web UI's nonlinear hypertext structure is user disorientation. Without physical borders, users are highly susceptible to aimless wandering. To prevent this, designers must manufacture a sense of place. This begins with a stable home base that acts as an anchor, coupled with recurring, predictable navigational toolbars on every single page. Complex content must be organized into clear, hierarchical tree structures. Distinct categories and subcategories prevent the user from being overwhelmed by flat lists of data. To maintain spatial orientation, visual feedback is required. Breadcrumb trails and sitemaps show the user exactly where they are in the hierarchy and detail the exact path they took to get there. Moving down to the presentation level, there are strict theoretical guidelines for hyperlinks. Embedded links must be visually distinct from decorative graphics, ensuring their interactive nature is obvious. There are also specific syntax rules for identifying link destinations. Links directing the user within the exact same page should be preceded by a hashtag, while links directing to external sites are preceded by an asterisk. Rigorous, standardized wayfinding prevents the user from having to actively think about how to navigate. It frees their cognitive load, allowing them to focus entirely on the information itself. Transitioning from macro site architecture to the micro-mechanics of a single screen, layouts are governed by the core UI principles of consistency and simplicity. Screen density and flow adhere to strict biological rules. Interfaces must minimize erratic pointer eye movement by forcing a logical top-to-bottom and left-to-right reading hierarchy. This dictates control placement. The most frequently used and critical information must be anchored at the top left, while command execution buttons are relegated to the bottom of the screen. This layout demonstrates how complex data entry is made logical through alignment. The white space surrounding the municipality and department sections creates separation. On the right, thin single-line borders and two-character position horizontal spacing establish visual rhythm, eliminating visual clutter. This distinction drives the user's mental model. Radio buttons signify a single, exclusive choice, while checkboxes indicate that multiple selections are permitted. All of these exacting layout choices, the spacing, the borders, the specific input controls, serve the ultimate principle of error prevention. The interface is designed to proactively minimize the chances of a user making an input mistake. Mastering interface engineering, from the psychology of an affordance to the millimeter spacing of a form box, relies on continuously answering the basic questions of goal-directed design. Who is the user? What is their exact task? And what do they expect to happen when they click?